How's it going, ladies and gentlemen? Mr. Donahue here once again. This time we're going to take a look at the equilibrium constant. So our objectives will be to determine the proper equilibrium constant expression given a balanced chemical equation, calculate the value for KEQ given equilibrium values of reactants and products, infer if an equilibrium lies far to the left or right based on the magnitude of the KEQ constant, and manipulate the equilibrium constant and determine the resulting value for KQ. Like if we were to flip the equilibrium and write it a different way, or double the coefficients, or combine some equations, what would our resulting KQ be? So let's start with an example equilibrium. So we got N2 plus 3H2 giving me 2NH3. So as long as you start with each reactant or product, you can achieve an equilibrium with this reactant. So at equilibrium, there's always going to be the same proportion among the reactants and products. So you can see on the left here, we started with NH3. So we have a significant amount of NH3 that we started with, and it declines until equilibrium is reached. And at the same time, we're producing H2 and N2 till equilibrium is reached. And then, we could start at it the other way. Instead of starting with NH3, we could start with H2 and N2 and no NH3. And you can see H2 declines over time. Same thing with N2, and NH3 increases over time. And they still meet the same kind of ratio regardless of which direction they started with once they reach equilibrium. So it's always the same ratio at equilibrium. So if this was my equilibrium, one blue equilibrium with one red, it's always going to be in the same ratio. So here I started with 8 blue, and then I ended up making 2 red. So now I have 6 blue. And it's always going to be this 3-to-1 ratio. So here I'm starting with 4 blue, but you can see it always is going to still be, it's still in this 3-to-1 ratio once it reaches equilibrium. I could even start with a bunch of red, and then what do you think is going to happen? Well, surprise, surprise, we're still going to reach this 3-to-1 ratio for this equilibrium. It's always going to be in that ratio. So KEQ, the equilibrium constant expression, is going to be this equilibrium proportion between the reactants and the products can be expressed mathematically as the KEQ. It's the equilibrium constant expression, or the equilibrium expression. So if this is my generic equilibrium where, big A, all the capital letters are different substances, and the little lowercase letters are the coefficients, the equilibrium constant is going to be the following. So it's written as KEQ, sometimes KC, the C for concentration, and you'll see that when we're dealing with solutions. It's going to be the concentration of the products, essentially. So C to the power of little c times D to the power of little d, all over the reactant side of things. Concentration of A to the coefficient of A times the concentration of B to the coefficient of B. It's basically products over reactants. Now for gases, instead of using concentration, it's usually pressure that we use, right? So it's KQ. Sometimes it's referred to as KP to specify that we're using the pressure. But it's the same idea, but instead of using concentrations, we're using pressure. So it's the pressure of product C to the power of the coefficient, etc., etc. Right? So just take a look at that. Hopefully it doesn't scare you. So this constant expression is going to depend only on the stoichiometry of the reaction, not the mechanism at all. So the number value will change with the temperature. If we raise or lower the temperature, we're going to change the value for KEQ. What it doesn't depend on is the initial amount. So KEQ doesn't matter how much we start with of what. And it doesn't matter if other substances are present as long as they don't react with the reactants in the products. So if there's no other substances chemically reacting with this stuff, it doesn't matter that it's there. So for example, right here I start with blue, and I end up making kind of this orange color. So I still end up with a 3-to-1 ratio. It doesn't matter how much I started with. It also doesn't matter if there's other substances there. If they're not chemically reacting, then it doesn't matter that they're there. So let's do a little practice. What is the equilibrium constant expression for the following reactions? I'll do the first one with you and then pause it and try to do the other two. So KEQ is going to be the products, right, over the reactants. So the products would be C, and it's going to be to the third power because of that coefficient of 3 there, all over the reactants. So I have A with a coefficient of 1, so it's to the 1 power, times B to the second power because its coefficient is 2. So that's what it is for the first one. For the second one, hey, this time we got gases. So it's going to look a little different. KEQ is going to equal the pressure of NH3 squared, because of this 2, all over the pressure of N2 times the pressure of H2. And that pressure of H2 is cubed. It's a terrible 3. Because of the 3 in front of the H2. All right, and the last one we have, again, aqueous solutions. So we're going back to using the concentrations. KQ is going to equal, all right, products go on top. So I got this H plus ion squared because of the 2 coefficient times the C2O4 ion. And that's going to be to the first power all over the H2C2O4 concentration, which is also to the first power because of the 1 there. All right, numerical values. So we got the expression. Hopefully we feel pretty good about figuring out what the expression is going to look like. So how do we get numbers for these KEQs? To get the equilibrium expression, you need to look at the coefficients. So the coefficients describe the ratio for the forward and reverse processes, not how much of each exists at equilibrium. I don't want you getting confused thinking that, all right, at equilibrium, it must be a 2-to-1 ratio. That's not how that goes at all. In fact, most of the time, it won't follow that pattern. You know, it takes 1 N2O4 to make 2 NO2, and it takes 2 NO2 to make 1 N2O4, but it doesn't mean at equilibrium this is a 1-to-2 ratio at all. And if you take a look at these different experiments, you can see at equilibrium, these are not 2-to-1 ratios at all. In fact, it's like more than a 10-to-1 ratio at equilibrium. So don't get confused with that. So first, determine the equilibrium constant expression. So if this is my equilibrium, you can figure out the equilibrium constant expression based on that. It's going to be the pressure of the product to the second power because of that 2 divided by the pressure of the only reactant there. So now to get the KQ value, you just pick one of these experiments. You know, they'll give you equilibrium values and you just plug it in. So I'm going to go with, I don't know, trial 1, because why not? So I take the pressure of the product, square it, right? I just plug in my values and then I get my KEQ value. And there you go. Just plug them in. So practice. 2HI is in equilibrium making H2 and I2 gas. At a given temperature, it's determined that at equilibrium, the partial pressures are for HI 0.202 atmospheres, for H2 0.0274 atmospheres, and I2 0.0274 atmospheres. What is the value for KEQ? So first step, figure out what my KEQ expression is going to look like. It's going to be the pressure of the products, H2 to the 1 times the pressure of I2 to the 1 all over the pressure of HI squared. So now I just plug in the numbers. Well, H2 is this 0.0274 atmospheres times pressure of I2 is coincidentally the same number, 0.0274 atmospheres all over, where is it, HI, 0.202 atmospheres, and that is going to get squared. So when I plug and chug and I get those numbers, I get 1.84 times 10 to the minus 2. So this is my equilibrium value, my KEQ. So what does the magnitude of KEQ tell us? What can we deduce knowing what the value is for it? Well, we know generically it's the products over the reactants. So if KEQ is significantly greater than 1, that tells us we have a lot more products than reactants. So we say that that reaction lies to the right, because if we're going from reactants to products and we get a lot of products, we say it lies to the right. All right, if it's significantly less than 1, then the equilibrium lies to the left. It means we have a lot more reactants than products at equilibrium. So here are 2 examples. All right, 10 to the 8, that is a really big number. So we know that it is product heavy. It lies to the right. right? Where this one, 10 to the minus 30, that's a really tiny number. That tells me I have barely any products compared to my reactants. So lies to the left. All right, so things we can do with KEQ. Sometimes, chemists get bored and they like to mess with things. Well, here are a couple of rules. Rule number 1, the KEQ of the reverse equilibrium is the inverse of the forward equilibrium. Rule number 2, the KEQ of a reaction that has been multiplied by a number is the KEQ raised to the power of that number. And 3, the KEQ for a net reaction made of 2 or more steps is the product of the KEQ for those steps. Now let's take a look at each one of these things. So the KEQ of the reverse equilibrium is the inverse of the forward reaction. So since equilibriums can be approached from either direction, the value for KEQ depends on which way the equilibrium is written. Whether it's written N2O4 makes 2NO2 or, the other way around. 2NO2 makes an N2O4. So it's the same equilibrium, it's the same process that we're talking about, but let's see what happens to the KEQ expression. Well, if we start with N2O4 and we make 2NO2, we're going to have the pressure of NO2 being squared in the numerator. And if we have it the other way, well, we flip that thing and it's the reverse now. Now we have N2O4 on top and NO2 on the bottom. So you can see the values are different. We end up with different answers just because we are looking at it from a different direction. So when you change the direction, you end up with the inverse KEQ. So if we write it one way, it's products over reactants. And if we flip it around, we end up with what was a reactants over our products. So it's just like this, right? So if 6.46 was written for the forward reaction, if I were to flip it around, I take the inverse and I get the KEQ for it in that direction. Practice. So the following equilibrium has a KEQ of 1.24 times 10 to the 2. Right? And then the question is, what is the value for KEQ if it's written this way at the same temperature? So in order to do that, you just, you flip it. You go, let me take the inverse of that. 1 divided by 1.24 times 10 to the second. And that's going to give me 8.06 times 10 to the minus 2. So that's going to be my final answer. That's all you got to do. All right, second rule. The KEQ of a reaction that has been multiplied by a number is the KEQ raised to the power of that number. So same kind of equilibrium. Let's see what happens. What's the difference between the left one and the right one? Well, we times the left one by 2 to give us the right one. So again, this is the same equilibrium that we're talking about, but this time the coefficients have been changed. So, this might have to be done in order to solve some kind of Hess's law type problems. So you might do this, and you'll have to know what to do with the KEQ. So what will happen to the KEQ expression as well as its value? Well, originally it was written as such, right? The pressure of NO2 squared over the pressure of N2O4 versus, well, hey, now the coefficients are different. So I end up with pressure of NO2 to the 4th power instead of the 2nd, and N2O4 to the 2nd power instead of the 1st. Well, how do we know to do that? Well, because the coefficients are doubled, the power of each value is raised to, is doubled. This effectively is squaring the KEQ because we had KEQ and then we doubled it, so it's the same thing as squaring that value. Right? So you can square the KEQ that you got, that they tell you it is, and then that's your new KEQ. So for this expression, the KEQ is going to be that 41.7, which is the original KEQ squared. Part 3, the KEQ for a net reaction made of 2 or more steps is the product of the KEQ for those steps. So here I got an overall reaction, and they want the KEQ, but they tell us here are the steps and the KEQs for those steps. Well, I can see when I combine those two, I'll end up with my resulting reaction, right? Well, let's see. Br2 is made in this first step, and it's used up in step B, so they cancel out. And you can see I'm left with everything in my equation now being the resulting equation. So everything is good to go. I know I can combine those two together, just how they are, and that'll give me my resulting reaction. So let's take a look at the KEQ expression for A. It's going to be the pressure of NO squared times the pressure of BR2 all over the pressure of NOBR squared. And then KB, or KQ for B, is going to be, same process. It's going to be the pressure of BRCL squared all over the pressure of BR2 times the pressure of CL2. So if I were to multiply these two together, you can see that the pressure of BR2 is going to cancel out. And if we take a look at the KQ expression we would get for the original equation that they're asking about, it's going to be equal to the pressure of NO squared times the pressure of BRCL squared all over the pressure of NOBR squared times the pressure of CL2. And then, hey, when I multiply these together, I get that very same expression. So I got to multiply the KQ values together. So this was 0.42, and this value is 7.2, and I didn't do that math already, so give me a second. And I get 3.0. So that would be my final answer. So messing with KQ, the equilibrium constant, again, these are three rules. The reverse equilibrium is the inverse KEQ. The KQ of a reaction that's been multiplied by a number is the KQ raised to the power of that number. And the KEQ for a net reaction made of two or more steps is the product of the KEQ for those steps. All right, so units of equilibrium constants. Long story short, KEQ has no units because you drop the units out when you put them into the KEQ expression. So long story long, the values we put into the KQ are actually compared to a reference value. So the reference pressure is 1 atmosphere and the reference concentration is 1 molar. So this effectively is just going to cancel out the units. So if we're taking a look at the equilibrium we've been talking about, if this was my equilibrium constant expression, it's actually going to be the pressure of that thing divided by the reference pressure. And the same thing for the reactants. So what you're doing is you're taking whatever the pressure was and dividing it by the reference. Effectively, it just cancels out the units. So 0.526 atmospheres divided by 1 atmosphere, atmosphere cancels out. 0.0429 atmospheres divided by 1 atmosphere, atmospheres cancel out. So you end up with a number that has no units. So equilibrium constant expression, no units. Takeaway, make sure your units are consistent before you plug them into the KQ expression. Don't have one be atmospheres and the other be torr or anything like that. And then you can just forget them. All the pressures are, make sure you use the same unit. All the concentrations use the same unit. So that's it. Summarize. Can you determine the proper equilibrium constant expression given a balanced chemical equation? Can you calculate the value for KQ given the equilibrium values of reactants and products? And can you infer if an equilibrium lies far to the left or right based on the magnitude of the EQ constant, as well as manipulate the EQ and determine the resulting value for KQ? For example, flipping the equilibrium, doubling the coefficients, etc. I hope you can. It's been a pleasure. Okay, bye.